Actually, I did. I was like,
I think when he was, I don't think he looked at us much now. He was really flinching.
It's like not real. Yeah, it's not real. Like there's a whole thing about like that's all psychological. You know, it's
That will make me.
All
right, page 5.
What you're doing. I think that you're good. You're still not doing.
yeah, there's no.
No matter what you need. Like I started.
I got psychological, it's an ethical realism and psychological.
Okay, so today we're talking about these word problems. These are really exponential growth decay problems. So what we're going to have to do here is there's going to be one differential equation that is going to be used for all these problems, but then they all turn into the same general equation. So really, once we understand that process, we can jump directly to the general equation. And because we're jumping to that general equation and skipping that derivative process or that integral process, a lot of these problems are just going to feel like algebraic problems. You're just solving for different variables, and then, but it's still considered AP Calculus content because of that little bit of solving differential equation at the very beginning. But a lot of times these problems just feel like algebra problems. There's not much calculus going on because we're already starting with the general equation that we know is going to show up. Okay, so just a little bit of background and review. Direct proportion equations are one where it looks like y equals kx, where y and x are directly related to each other. K is called the, or sorry, and then K is called the constant proportionality. And then inverse or indirect proportion is y equals k over x, where y and x are in the numerator and denominator on opposite sides. But typically, most of our equations are going to hang out in that direct proportion equation form. Okay, so this is really the only calculus that's going on. But once we build this general equation, it's just going to be the one that keeps showing up. So it says if the rate of change of y, so we can call this, what is that? What variable can we call this?
Y prime.
Y prime, yeah. So y prime varies directly with the value of y. So that means the direct proportion. So y prime equals what? K times with the value of y. So y prime equals ky. Yeah. So whenever you see this type of differential equation relationship, you can jump directly to the general equation, which we're going to arrive at. But once we arrive at that, then as long as you know that there is that relationship, you don't have to go through that whole calculus process anymore. But we'll do it for one time so you can kind of see this kind of working out. So now with growth decay problems, these are all going to be involving time instead of x as our independent variable. So in this case, it will be dy over dt that we're starting off with. Okay, so I am going to separate the variables. I want my dependent variable, anything involving with y's on the left, and then everything else on the right side, including my independent variable t, and my constant k is still the leftover. So leftover, anything is going to be on the right side. The left side, we want to typically leave as minimal as possible. So I'm going to cross multiply here. All right, so we want full separation of variables. Is there anything out of place?
Y.
The y. So what do we do with it?
Divide.
Divide. So if we divide it, it ends up in the what on the left side? the left side, denominator, that's right. To make sure we leave that y in the denominator. Typically, I see what some students do is they just divide it, but they end up kind of letting it float up to the top. So if algebraically, if that's where it ends up, that's fine. But in this case, algebraically ends up in the denominator. We need to leave it there. Okay. All right, I'm going to set this up so that we can clearly see the integral rules that we're going to use. Now, the k is not going to change. Okay, k is not the variable here. T is the variable. So k can stand outside the integral. If you want, you can put a 1 dt as a reminder that it's the 1 that's getting integrated, not the k. So we don't want to say k squared over 2, right? That k is just a constant. It's going to hang out in front. Okay, so let's go through the rule here. What's the integral of 1 over y dy?
Natural log of absolute value.
Okay. The k is going to stay. 1 becomes what?
T.
Good. Yeah. So our independent variable is t. So the constant will rise up to a degree 1. So kt plus c. Okay. Everybody okay so far? All right. I want to solve for y. So to solve for y, I'm going to involve base e. I'm done with the calculus. I'm just trying to get y by itself. E and natural log are going to cancel each other out. I'm left with absolute value. Y is equal to e to the kt times e to the c. So e to the kt times e to the c. We know e to the c is just some large constant. But now it's getting multiplied. I can drag that constant in front. I'm going to drop the absolute value. The plus or minus is going to get absorbed into the c. So I have y is equal to c e to the k. T. So this is the equation that's going to show up again and again. As soon as you see rate of change of a variable varies directly with that variable, you can jump directly to this equation. We don't have to go through this whole thing again. The only thing that's different is that the variable involved could be different. So we're going to see population, we're going to see radium, we're going to see different variables here, but it's always some dependent variable. And then our independent variable is always going to be time. Okay. Okay, so let's look at number 2 here, the rate of increase of population. So what can we notate that as? P
over dt.
P prime, yeah, dp over dt or P prime is proportional to the population. So P prime equals K times what? KP. So this is the same form, right? Y prime equals KY, P prime equals KP. We don't have to go through this whole thing. We can jump directly to this, right? We already know, okay, this is our general equation, and we're skipping all the calculus step because we already know where it's headed. So, this is the only calculus step in all these problems, and now it just turns into algebra problem where we're just doing a bunch of substitutions. Okay, now to help us organize all these numbers that we're going to be dealing with, because we have to solve multiple variables, right? We got to solve for K, we got to solve for C, and then we're going to have to make a population prediction. So I like to organize all my information as ordered pairs. So as ordered pairs, my time is my independent variable. So in this case, I'm going to treat time as my X value. And then whatever the other variable is, that's my dependent variable. That's my Y variable. So everything I'm going to organize as T, comma, P. Okay, let's create a bunch of order pairs here. We got population in 1930, it was 50,000. In 1960, it's 75,000. What's the expected population in 1990? To make it easier so that we don't have to worry about how to deal with these large year values, let's just find the earliest year value and let it be t equals what? 0. Yeah. So we're going to let 1930, or sorry, let t equals 0 represent 1930. It'll just be a lot easier with the substitutions. Okay, so that means at year 0, what's my population?
50,000.
50,000. Okay. In 1960, 75,000. So how many years after year 0 is that?
30.
30 years. So 30 years later, 35,000. And then what's the expected population in 1990? 60. So we're ultimately looking for 60 years later, what is my population? Now, usually the order of problems is not always the case, but usually we want to take advantage of that zero. That zero is going to help us clean things up. So this is usually going to help us solve for C. And usually the order is we find the C value, we update the equation, and then we use the other order pair to find the K value. We update the equation, and once we have the specific equation, then we can use it to make further predictions, give it a T, and find the P. So I'm going to start with this 0 50,000 here. Basically, it's going to be the C value, but I'm just going to go through the substitution process, because if the equation looks a little bit different than this, then this C value may not always be that number. So 50,000 in for P equals CE to the K times 0, right? I'm just substituting 0 in for T and 50,000 in for P. E to the K times 0, that's nice. E to the 0 is just 1, that's going to wipe out. So C is just 50,000. So I'm just working my way from general to specific. Okay, so now I'm going to update my equation. I have my C value. So P is equal to 50,000 E to the KT. So I have a second order pair that can help me make additional progress. So 30 plugs in for T and 75,000 plugs in for P.
We have calculators.
Yes, you'll get to use calculators. Now, it's important that as we solve for K, that we leave our answer in exact form. Okay? In the end, in the very, very end, you are going to approximate to 3 decimal places, but we don't want to make any approximation at this middle stage, because if we do, then we take away from the accuracy of the end product. So we do want to hold on to that messy exact value for K, and then we get to the very, very end, then we can do 3 decimal places. But here, we're going to try to leave our answer in exact form. So I want to solve for K, but first let me try to get this expression by itself. I'm going to first start off by just moving the thing that's easiest to move. I'm going to move that 50,000 over. Okay, we're going to reduce 75,000 or 50,000 can reduce to be 1.5. All right, I want to solve for K, but K is stuck in the exponent. What can I introduce to make it easy? Yeah, so natural log allows E and natural log to go away, but also allows my exponent to come down because of exponent properties. We know natural log of E goes away. That's nice. So natural log of 1.5 equals 30K. Divide both sides by 30. Okay, so we do need to hold on to this exact value. So don't do decimal here. Okay. So now we have our exact equation. We have our C value resolved. We have our K value resolved. And now we just have to make our final prediction with the answer. So let me rewrite my equation here. P is equal to 50,000 E to the natural log 1.5 over 30 E. All right, so now I can find my predicted population 60 years later, or in 1990. So I can plug 60 in for T, then make my calculator plug all this in, and then I can do 3 decimal places. So in 1990, the predicted population based off of this relationship is 112,500. Okay, so confirm, make sure that you can get what I got in your calculator. All right, minimal calculus here, but because we're skipping all that step from here to here. Okay, let's go to the next page, page 6.
That's it. Half is becoming exactly 112,500. It's like.
Yeah, I think in my calculator it came out to be some 0.00 something, so I just rounded it to.
Okay.
Yeah. All right. The rate of decay of radium, so R prime, is proportional to the amount present at any time, the amount of radium present at any time. So R prime equals KR. Same relationship, right? Y prime equals KY, P prime equals KP, R prime equals KR. We know we can jump to this equation. All right, so I'm going to organize my order pairs here. My independent variable is always going to be time, and whatever the other variable is, that's my dependent variable. So if 60 milligrams of radium are present now, so let's consider now as year 0. So year 0, 60 milligrams of radium. Its half-life is 1690 years. So 1,690 years from now, how much radium remains? 30, so half-life. How much radium will be present 100 years from now?
Plugging in 0, can I just get those?
Yeah, you can skip that step, especially if you're dealing with this equation. You can skip this step. Now, if you're dealing with a different equation, then you do want to make sure you spend the time. But yeah, you can skip the step if you like. You know what's going to happen. Okay, so work through the problem, similar steps, see if all this makes sense.
Have to include units of measure.
Yeah, milligrams. Everybody okay with 3? Okay, number 4. In a certain culture where the rate of growth of bacteria, so I can call that B prime, is proportional to the amount of bacteria present. So B prime equals KB. We know it's going to be that same equation, right? Use those here. Okay, I like to organize my information using order pairs here. So we have some initial amounts, right? And then that initial amount is going to triple in 3 hours. I don't know exactly what that amount is, but I do know that at time 0, I can let C represent my initial amount, right? So at time 0, there's some initial amount of bacteria. 3 hours later, what's going to happen to that number? If at the end of 12 hours, there were 10 million bacteria, so we'll just let 10 represent millions. So at the end, we have to multiply our answer by 1,000,000. Okay. How many were present initially? So the first equation is not going to help make any progress, right? We're not going to get anywhere. But this next equation, let's see where that leads us. If I replace 3C in for B, I can solve for K, right? Because the C's drop out. So the problem is asking for the amount present initially. You're not going to solve for C first. You're going to solve for K first and then work backwards and then eventually get to your C. Okay, next step. We're going to solve for K, so take the what of both sides. Hold on. Okay, let's update our equation. So I'm gonna now I'm gonna solve for C by plugging in 12 in for T and 10 in for B, and then I should be able to get to C from there. 10 divided by e to the 4 natural log of 3. Point 123.
But you're approximating it early though. You keep it exact.
I'm sorry.
Do you keep the C exact or approximate it early? Because and the other problems.
Well, this is my answer. So this is, I'm looking for C. So my middle step was the K. Yeah, so this is fine.
I don't know. I was thinking like go back to equation plug in 0, but it.
Oh, right. No, yeah, we're good. So multiply this by 1,000,000 and we get 123,000. So 123,456 bacteria. Okay, any questions? Okay, let's continue picking out problems from the test review. Page 4. Okay, so page 4 in your packet. Everybody good here? Okay, h of x is the integral from 6 to x of f of t. I'm just going to go ahead and build out my derivatives, have everything in front of me. Okay, so h is just the area under the f graph. H prime is just the order pair of f itself. H double prime is just the slope of f. All right, so let's find h of 0. H of 0 involves the region between the graph and the x-axis. I think it's always a good idea just to shade very lightly between the graph and the x-axis, so you're never accidentally getting the wrong area of a wrong region, right? I know there's different shapes here, but we only care about the shape that's between the graph and the x-axis. I want to read the graph from left to right, so I prefer my bounds to be in order. Right, so it's just a bunch of triangles and rectangles.
Oh, that's all. So, 6. 5.5. That's nice. That's like.
Okay, A through D just involves the region between the graph and the x-axis. I only had to flip the bounds for A, the other ones are all in order. Okay, H prime of 3. Just the order pair of the F graph. Uh-huh.
So for E, you just plug in the 3 for T.
Yes, because I know that H prime of X is F of X, so.
So like it's like the f of x and f of t function the same.
Well, because we went through second theorem says plug the upper bound into the variable, so this becomes F of X times 1, so it turns to F of X,
Okay.
right? Second theorem.
So like, is there any difference between the f of t and
Not after.
Yeah.
Right,
different?
right. Yeah, you're right. Right. Yeah, F of t and F of X are the same. It's just that for notation purposes, they do want this upper bound and this bound variable to be different,
Okay.
different variables. Yeah. Okay, H double prime of 9.5 translates to F prime of 9.5, and that is simply asking for the slope of the graph at 9.5. It feels like a strange decimal there, but it's the same. We know that anything on this line is going to be the same slope. So if I can find the slope of this line, I can find the value of S. So I can go up 3 units to the right 3 units. So my slope is just 1. For part G, for what value of X is H increasing? So this is F, this is H prime basically, right? This is H prime. So we have to kind of remind ourselves that we're looking at the derivative graph, so we can label accordingly. Create our slope sign line, and then once we look at the movement of our arrows, we can decide where our relative max and relative mins are. So we know that our critical points are at 1, 6, and 10. Negative slope, positive slope, negative slope, positive slope.
10 past 50 or
I'm sorry.
10, 11? Is there like, because on the graph, there's like an arrow.
Oh, I had that being a endpoint.
Oh. I thought I saw.
Okay, for what value is H prime decreasing? So this is really talking about the slope of H prime, right? So we're looking for this value, 4 to 8. Okay, last part, find the absolute extrema. So absolute extrema, we go to our slope sign line. This is EVT, extreme value theorem. And we just test our endpoints and our critical points. Right, so we'll test 0, we'll test 1, we'll test 6, we'll test 10, and we'll test 11 because 1, 6, and 10 are all valid because these are all relative max or mins. I think some of it we've already gathered from above, so.
For G. Find the absolute extreme of G.
Oh, it should be
H.
It should be H, my bad, H. So there's not, you don't have to write out because statements for EVT. You just have to show me that you are testing all the valid critical points, endpoints and critical points, and then you're making the appropriate conclusion. Just tell me the Y
You
value.
don't have to state that's continuous on 0.
Nope. Yeah, technically yes, but on the if it's like a free response type questions, they're not asking for that justification. So on the AP exam, you can just write out your write out your test points and then make your conclusion. Okay, tomorrow is your test, calculator portion. Tomorrow morning, I will have a help session at 7:15. I'm going to go through pages 11 and 12, but I encourage you guys to try them on your own, right? Just especially with the calculator type questions involving all the keystrokes. I will put out, if you are stuck you know, because we're still kind of getting used to the calculator, so any keystrokes that you need, I'll go ahead and put those on the board. If you're wrestling with, wait, how do I get to n deriv or math 9, right? But I do encourage you guys to practice tonight, and then tomorrow morning, run through it again with me in the morning. Yeah.
Just like 3 times those.
That's right. So you're going to see a particle motion problem. You'll see a derivative problem that we just did. And then you'll do Riemann sums, table of values that we did yesterday as well. So particle motion, Riemann sums, derivative graph. Okay. All right, complete your phones.
So, I think I got this analysis. So, you looked at velocity.
We look at velocity and acceleration because it's a speed increase.
Okay, so,
If it's saying is the velocity increasing or decreasing, then you should look at acceleration.
so to justify that, I have to agree for it to be increasing or how?
Your velocity acceleration have to be either the same size or opposite size.
Okay.
If they're the same size, increasing. If they're opposite size, then the speed is decreasing.
If they're different,
If they're different, that's opposite sides, yeah.
So, yeah.